Hi, my name is Hannes Kirsten and today I will be talking to you about my research paper, Digging for Gold in Sharp Minima, specifically with regards to neural network loss landscapes. Here is a summary of what we will be discussing. We will start with the background in neural networks, fitness landscape analysis and sharp and flat minima, and then go on to regularization and pruning. And then we will discuss our hypothesis, and after this we will look at our experiments and results. Let's start with neural networks. Neural networks are a machine learning technique that uses the concept of a brain with neurons that get activated based on certain input, and in the end it will provide us with an output or a prediction. It can be optimized using the backpropagation algorithm, which will adjust the weights slightly as the neural network gets trained in order for it to improve with its predictions. Here is a very simple example of a neural network. On the left-hand side, we can see our input neurons. Each of these will be provided with some value that we want to make a prediction on. These values will be used together with some weight value to calculate the value for the hidden layer neurons, and this process will continue until we reach the output layer, where we will be able to make some prediction based on the input that we started with. The weights that are used together with the neuron values in this calculation will then be adjusted slightly during the training process in order for the output to be more accurate based on the provided input. This is a very powerful process since this complex, almost black box-like behavior can make very complicated calculations that we would otherwise not be able to understand or recreate ourselves. The next important concept for this research paper are fitness landscapes. We will discuss fitness landscapes in general before we start looking at neural network landscapes specifically. A fitness landscape is the landscape in which a machine learning model is optimized. When the weights or values of a certain machine learning model is slightly changed or modified, we will be traversing this landscape by increasing or decreasing our fitness value, or in the case of neural networks, the loss value. This concept was originally introduced by Sewell Wright, who mentioned this in his paper on genetic evolution and how changing a gene can increase or decrease the survivability of a species. Here are some visualizations of fitness landscapes. Fitness landscapes usually require a lot of parameters to be set. In the case of neural networks, it can be thousands or even millions of parameters. So visualizing it as a 2D or 3-dimensional landscape is impossible. But just to get a basic idea, on the left-hand side, you'll see a landscape in 3 dimensions, where if you are at some specific point on the landscape and you change your X or your Y value, you will either increase or decrease your fitness value. On the right-hand side, you can see a one-dimensional model where only one parameter is adjusted and the error value will increase or decrease. This also shows us what it will look like when a neural network or some other machine learning model is optimized, where we calculate in which direction we need to move in order to decrease our error value. In this case, we find the derivative of this function and see in which direction we need to move down. and take small steps until we converge to the bottom of the basin. This is where we can introduce another important concept for this research paper, sharp and flat minima. When we converge towards a minimum in our fitness landscape, it can be a sudden, sharp convergence, or it can be a slow convergence that takes a lot of steps to reach the bottom. On the right hand side, you can see the visualization of what it would look like to have a sharp basin with a sudden drop in error value, or a wide basin where the error decreases slowly as a model is optimized. The last important concept for this research paper is regularization, which is somewhat of a different topic, but all that this means is simplifying a neural network or some other statistical or machine learning model in order for it to generalize better, meaning that when we train it on a set of training data, it will also perform well on previously unseen data that was not part of training. If this method is not applied, some methods might end up being very accurate on the training data, but on real world data, they will start to lose accuracy. There are a bunch of different techniques for regularization, such as L2 and L1 regularization, dropout, or data augmentation. But the one that is interesting for this paper is pruning, meaning that a neural network will be stripped of all the weights that are not important for the final solution in order to smooth out its predictions, and in doing so, we will improve generalization. For a long time, it has been believed that sharp minima are a bad thing and that it leads to bad generalization. But more recent research has shown that this might not always be the case, and that sharp minima in some cases might actually generalize better. We have an hypothesis that is not based on generalization but rather regularization. We state that neural networks that end up in sharper minima will regularization. This is because we think that if a neural network ends up in a sharp minima, it might be because it had to use less weights to get that optimized solution. And having less weights that are actively contributing to the solution means that it is a simpler solution or more regularized. To test our hypothesis, we will be using the four sharpness measurements: average sharpness, max sharpness, Hessian trace, and top Hessian eigenvalue. To calculate the average and max sharpness, we start at the minimum that we ended up in for our optimized neural network, and we choose a random direction, and we take steps in that direction and in the opposite direction. At each point, sampling the loss value at that point. After we did this, we do it for a few more random directions, and then we will look at the average increase in the loss value as we walk away from the minimum, and the max increase as we walk away from the minimum. We will be taking 10 steps in the positive and negative direction for 30 random directions. For the Hessian trace and the Hessian eigenvalue, we will be using a library called PyHessian that estimates this Hessian trace and Hessian eigenvalue, since it is computationally infeasible to calculate when using millions of weights in our neural networks. This measurement is a representation of the second derivative of the neural network solution, meaning that it will show us how sharp the curve is at the point of the minimum. And generally, this is more an indication of jaggedness or local sharpness, more than it is of the global attraction basin. To calculate regularization for our neural network, we will be using the parameter distribution and looking at how many of the parameters have very small values that contribute very little to the final solution, since having more values that do not contribute to the solution means we have a simpler, more regularized solution. The first measure is the percentile values of the parameters, meaning we will look at what the parameter value is for the 5th, 10th, and 20th percentile of all the weights in our distribution. The second measure is the threshold measure. We will count how many parameters have a value less than 0.01, 0.001, and 0.0001. This will also indicate to us how many of the parameters are very small and almost insignificant. To conduct our experiments, we will be using different datasets and different architectures to see what the correlation between sharpness and regularization will look like for bigger networks and smaller networks, as well as different types of networks, such as the normal multi-layer perceptrons or the convolutional neural networks. This table indicates the different architectures that will be used and how many layers each of them will have. Here are some of the hyperparameters that will remain constant throughout our experiments. For each architecture and data set, we will be training 100 neural networks for 100 epochs with a learning rate of 0.01, and the learning rate will decay at a rate of 0.9 at each epoch. We will be using the Adam optimizer algorithm and the cross entropy loss function, as well as the ReLU activation function for our hidden layers. Here is the first of our 4 results tables, each showing the results for one of our 4 sharpness measures. On the left-hand side, you can see the architectures used to run our experiments, as well as the data sets that they trained on. At the top, you'll be able to see our regularization measures and how they correlated with our sharpness measure. The R values are the correlation coefficients, a value between -1 and 1, indicating if there was a negative or positive correlation and how strong that correlation was. The P values indicate our confidence in this correlation coefficient. A lower p-value means we have more confidence that this correlation coefficient is correct. We want a p-value of no more than 0.05 to indicate a confidence of 95% or more. As you can see, for our smallest neural network, the MLP1, meaning a normal standard neural network with one hidden layer, got no correlation at all, with no confidence in our correlation coefficient and a very low correlation coefficient. For the MLP4, you can see we have a much stronger correlation coefficient of between 0.6 and 0.7. This means that there is definitely a correlation between sharpness and our regularization metrics. Unfortunately, having a positive correlation with our percentile measures and a negative correlation with the threshold measures means that our hypothesis was incorrect, since a higher number of weights below these thresholds would mean better regularization. But as our neural networks get sharper, they seem to have fewer weights that are very low, indicating worse regularization. And this is the case for the MLP4 on the MNIST dataset, as well as the MLP on the fashion MNIST dataset, as well as all of the results on the CIFAR dataset, with the only outlier being the small CNN, showing a positive correlation with the threshold measures and negative with percentiles, backing our hypothesis. But as I'll show you in the next slide, this is not a reliable result since the results still seem to be pretty random. For the MLP4 fashion MNIST, you'll see again a very weak correlation. But as we get to the MLP9, which is a normal neural network with 9 hidden layers, we can see an extremely strong correlation, meaning that when we have deeper neural networks with more hidden layers, we seem to get stronger correlations with regularization. When it comes to the convolutional neural networks that are pretty big architectures, it seems that the correlations get a bit weaker again. And in the case of the small CNN and possibly AlexNet as well, the correlations probably don't have a lot of meaning. But at least with the small CNN on the CIFAR dataset, there is still a stronger correlation. Here we can see the correlation plot of the outlier that we saw on the previous slide, with the small CNN on the MNIST dataset. We can see that as average sharpness increases, our regularization increases as well. But this is still very random, and it seems that most of the results, other than the few outliers, are pretty spread out, meaning that the opposite behavior for this neural network might not be very reliable. Here is an example of a correlation plot for the MLP with 9 hidden layers, where we saw the strongest correlation. As you can see, when the average sharpness goes down, there is a very clear correlation with regularization increasing. Here is our second results table, showing how max sharpness related to our regularization measures. As you can see, we still got no correlation for our small neural network, while the rest of the results seem to be very similar to the results of the average sharpness, with the one notable thing being that they are all slightly less correlated with max sharpness than average sharpness. Now we get to the Hessian measures, with the Hessian trace showing some interesting results. With the smallest networks, we can see that we almost have a slight correlation now, even though it is still very weak, and the MLP4 on the MNIST is much stronger than it was on the average and max sharpness measures. And here we can see the small CNN still shows the opposite behavior, but this time the other two CNNs seem to also show opposite behavior, with the small CNN on the CIFAR dataset having a very weak correlation, but both the AlexNet and the small CNN on the MNIST dataset show that there definitely is a correlation that behaves in an opposite manner to that of our normal multi-layer perceptron neural networks. This is very interesting, and this might be because Hessian tends to measure jaggedness of the loss landscape more, maybe indicating that convolutional neural networks behave better when they have jagged surfaces. Here is the last results table for the Hessian eigenvalue. This one has very similar results to the Hessian trace and still indicates that the multilayer perceptrons have a negative correlation, while the convolutional neural networks have a positive correlation with regularization. This time, the small CNN on the CIFAR 10 dataset has a slightly stronger correlation, but it is still very weak. Here we can see an example of a correlation plot on the AlexNet for the Hessian eigenvalue and the 0.001 threshold. And as you can see, this positive correlation is very visible, but it is still not extremely strong. In conclusion, it seems that in general our hypothesis was wrong, and that sharpness tends to have a negative correlation with regularization. But this is not without some strings attached, where we saw that with small neural networks, sharpness did not seem to influence the regularization of a neural network. And in the case of convolutional neural networks, we did see some results that backed up our hypothesis, especially with the Hessian trace and Hessian eigenvalue sharpness measures. This is a very difficult topic to discuss, and there is a lot of ways to interpret these results. Hopefully some future research can help us get a better understanding on sharp minima and regularization. Thanks for watching, and I hope you found this video interesting.